The title of our work is DYSON Dynamic Feature Space Self-Organization for Online Task-Free Class Incremental Learning. I'll explain our work in these three parts. OTF-CIL is a subfield of class incremental learning. Taking continuous data streams as input, online task-free class incremental learning (OTF-CIL) aims to incrementally learn newly emerged classes by online learning without task boundaries and identifiers. The classical class incremental learning splits a data stream into a series of subsets, namely sessions or tasks, where each subset contains the samples of certain classes and different subset classes are mutually excluded. The OTF-CIL is a practical but more challenging problem, wherein the samples are one-shot provided and old and new class knowledge are blended. Neural collapse is a theory proposed in 2020. It can be summarized into 4 steps. First, the within-class variation of the activations become negligible, as these activations collapse to their class means. Second, the factors of the class means after centering by their global mean converge to symbolic ETF. Third, the class means and linear classifiers converge to each other up to rescoring. Fourth, the network classifier converge to choosing whichever class has the nearest chain class mean. The definition of the EQF is having equal lengths, forming equal-sized angles between any given pair and being the maximally pairwise distance configuration constrained to the previous 2 properties. It can be calculated using the formula below. Currently, there is work that applies neural collapse to the field of few-shot incremental learning. However, the theoretical research on neural collapse is based on static data scenarios. In the context of an incremental learning dynamic data environment, it does not fully adapt. Therefore, we have extended the concept of neural collapse to derive a DNC that is suited for dynamic data scenarios. First, during incremental learning, the symbolic ETF can be extended with the QI decomposition of class means, where P represents the set of class means that the model has learned. Z represents the symbolic ETF, which stands for prototypes. Second, the expansion of categories leading to the ETF deviation has a finite upper bound, where Zi represents the ETF point before expansion, and Zi apostrophe represents the ETF point after expansion. There is the model structure of our proposed DYSON. It contains a feature extractor, a dynamic feature geometry alignment module containing a projection layer, and a training-free class incremental classifier. The core of this model is the DFGA module. During the training phase, DFGA first dynamically update the class mean factors, then do QI decomposition on the class mean factors, and computing prototypes according to the definition of ETF. Subsequently, the DFGA module obtains the alignment rules, which is used to help supervise the updating of the projection layer in the model. The overall rules of our model is the sum of the alignment rules and the cross-entry rules. According to DNC2, at the early learning stage when class number k is small, the class prototypes in Z are fair distributed and the shift distance of all the class prototypes are large. This results in the geometry being unstable in maintaining old knowledge. To improve the geometry stability during the incremental learning process, we introduce prototype placeholder to the DNC, where M is the number of placeholders, and then compute the class prototype with the padded pipad. When k is larger than or equal to M, we directly compute the prototype using P. We conducted experiments on 4 datasets, namely CIFAR 10, CIFAR 100, Core 15, and Cube 200. Next, I will present the experimental results of DYSON. First of all is the OTF-CIL performance in terms of last accuracy. From the table, we can see that the DYSON is a memory buffer-free method that does not require storing any old class samples to alleviate the catastrophic forgetting. The proposed DYSON method significantly and steadily outperforms the state-of-the-art methods by a large margin. Then is the performance of online class incremental learning and the performance of offline task class incremental learning. We have conducted ablation experiments on 2 aspects. Firstly, we conducted ablation experiments to analyze the influence of parameter M on last accuracy. Secondly, to get rid of the concerns that the new classes in the 4 benchmark datasets have already been learned by the ImageNet pre-trained model, we conducted an ablation study using a self-supervised DYSON 15 backbone. Finally is the conclusion of our work. Thank you.